Okay, we are discussing on Routh criterion, Routh-Hurwitz criterion for analyzing the stability of the system. Okay, right. Okay, so there are two. If all the elements in the first column of a Routh array is positive, means the system is stable. When there is one single sign change, means the system is unstable. So that we discussed in the previous lectures. So there are two special cases in Routh criterion. One is what happens if one zero appears in the first column. Okay, this is special case one. Second one is what happens if all the elements in the rows are zero. Okay, so there are two special cases for that. How to find the stability we discuss upon. Okay, if there is 1 0 in the column, the row element, means we have to substitute that zero. We have to replace the zero by epsilon, some common unknown variable epsilon. Then start proceeding as it is. Okay, then calculate the value of a C1, C2, C3, keeping epsilon as that number. Okay, so in the next term we are having 4 epsilon minus 12 by epsilon. So here limit we have to at the end, so keep on prolonged, we have to continue it. Okay, then look into the elements in the first column. Okay, for epsilon, substitute epsilon as a 0, then what is the value of s squared term, whether it is positive or negative? Based on that, we can decide the stability of the system. Okay, this is special case 1. In special case 2, if all the elements in a row are 0, means what we have to do is we have to uh, differentiate that equation. Okay, for example, we have to take the previous row. This is 7, s power 4 is 7, s power 4 42 s squared. So this is not s cube, this is s squared, because we are writing the coefficients of alternate terms. So 7 s power 4 42 s squared plus 56. So we are getting equation like this. For this polynomial, take a differential derivative. You have to take a derivative. So we have to take a derivative and put the values here. So here, if you take a derivative, we'll get. So here, all are multiples of a 7. So we can divide it throughout. So look into the second row. That is, we are dividing the common term by 7. So 1, 6, 8 we are getting. In the next row, if we differentiate this, we are getting 4s cube, 12s plus 0. 0 is constant term. Okay, 4. 4 and 12 are common. So there are 4 and 2 are the elements in that row. So we can divide throughout by 4. So we are getting 1 and 3 here. Okay. So after getting these two elements, and we have to proceed finding the elements in the Routh array, right? So 6 minus 3 is by 1 is 3, 8, 1 by 3, 0. Now look into the elements in that first column, all the elements are positive. There are no sign changes. So there are no poles on the right half of the S-plane. The system is stable. If the poles are on the right half of the S-plane, then system is unstable. If it is on the left half of the S-plane, the system is stable, right? So this is the second method, second special case. Okay. So taking one more example, finding the value of Kc, find the values of the controller gain Kc that make the feedback control system of the equation. The equation is given. All the coefficients are positive. And that is 1 plus Kc is greater than 0. That means the Kc is less than -1. Okay. Now start writing the element 10, 8, 17, 1 plus Kc, B1, B2, C1. Okay. To have a stable system, okay, Routh array must be, each element in the first column must be positive. Element B1 will be positive if Kc is this value. So element B1 will be positive. If that is uh, that is 10 into, if we divide this value, we'll get term like KC value will be 12.6. So similarly, C1 will be positive, KC is -1. Thus, we conclude that the system will be stable. See, look into this C1. So the system will be stable if the KC value is between -1 and 12.6. Right. So if we keep on working, if we keep on equating for 17 into 8 minus the 10 into 1 plus KC by 17. Okay, what is the value of KC? We have to find out. Because in that case, we're getting 12.6. So KC value will be minus 1 to 12.6. Okay. Thank you. We discuss root locus in the next class.